Okay, continue section 13. So when we left off at the end of the last class, I was right here. It says expressions involving CV, CP, and R. And I was kind of in the middle of working my way through that. The last thing that I had done was I had said that, I don't want that, I'll fold it. I had said that for any process involving an ideal gas, the change in the internal energy of that gas is equal to NCV times delta T, where CV is the constant volume molar specific heat. And that constant volume molar specific heat, if it's a monatomic gas, such as helium, any sort of atomic gas, 1 atom per molecule, it's 3/2 the gas law constant. So the gas law constant's 8.314 when you're measuring in SI units, joules per mole per degree. And so CV for that kind of gas would be something a little over 12 is what this is saying. So I came up with that by considering a constant volume process, among other things. So another nice relationship comes from considering a constant pressure process. Once again, I'm going to start with the first law. Change in the gas's internal energy is the heat added plus the work. Now, work is as is usually the case, we're going to consider just an infinitesimal change in the state of the gas, because otherwise you get involved with pressures that are changing and temperatures that are changing. And what do you put in for things like P and T? You know, what number do you put in there if it changes? So if the change in volume and temperature and all those things approaches zero, then you don't, then you get around that, okay? So an infinitesimal change in volume, the amount of work, which I guess really should be dW, is equal to minus P times dV. Now, gas law. I want to get this in terms of temperature instead of in terms of these things, but that's a dV and that's a V. So what I have to do is take the differential. Now the volume is constant. Otherwise, you'd have to use the product rule. It would be P times dV plus V times dP in general. But since we're talking, or I'm sorry, it's the pressure. The pressure is constant. Since the pressure is constant, we can just treat that P the same as if it was a 17 or something like that. And so P times dV is what you have to the left of the equals. Likewise, N and R are also constants, so they just sit there. And so in this case, when it's a constant pressure, the work done would be equal to minus NR times dt. So I've got that to put in there. Now, previously, on that piece of paper I flashed from the previous class, I had said that the change in internal energy is N times CV times the change in temperature. And, well, Q is equal to NC times the change in temperature. And since it's a constant pressure process, you'd have to use CP. So Q equals NCP times that. And then I've just come up with this substitution to put in for the W. And then quite a few things cancel out. You divide both sides by n. N over n is equal to 1, and we're rid of that. Divide both sides by dt. And dt divided by itself is equal to 1, and we're rid of that. And so we've got CV equals CP minus R, which, rearranging it a little bit, that's usually written as R equals CP minus CV. And I made no assumptions in any of this about what kind of gas that was. That doesn't have to be helium. That could be methane or carbon dioxide. If it's a monatomic gas, if it is helium or argon or one of those, then I had said right at the end of the previous recording that CV is equal to 3/2 times the gas law constant. Add that to both sides. For a monatomic gas only. For other kinds of gas, CP would take on different values. But for a monatomic gas, the constant pressure molar specific heat should be equal to 5/2 times the gas law constant. And there again, if you go and measure it, that is in fact what you find is true for helium or argon or neon or those sorts of things. And I already had explained during the previous recording why this is more than CV. It's because some of the heat goes into doing work in this case, whereas it all goes into raising the temperature in the constant volume case. So maybe I should emphasize, I already said this, but at least I think I did. I want to emphasize that this 3/2 R for CV and 5/2 R for CP is for monatomic gases. The values for CP and CV they vary for polyatomic gases. And you go to the table in the back of the reference handout and you'll find that if you have, it's kind of divided up into 3 groups. You've got the monatomic gases, and they're all pretty much the same. You've got the diatomic gases, and they're all pretty much the same as each other. And then it's got another one for more than 2 atoms per molecule, and they're fairly similar to each other. So, you know, if you get a problem that involves carbon dioxide, don't just stick this in there. Go to the table and look up carbon dioxide, is what I'm trying to say, I guess. Okay, so I think that takes care of the expressions involving CV, CP, and R. And of course, all this stuff's on the formula sheet. I've already said that. We'll do an example, and then we'll go on. The heat needed, and actually I probably could have done this back up in there, but it doesn't matter. How much heat is needed to raise 2 moles of helium? Part A. 2 moles of helium by 100 degrees, first of all, at constant volume. Well, in general, Q is equal to N times C times delta T, capital C, not that it really looks that different than a lowercase c when it's somebody's handwriting, but capital C for the molar specific heat. And part A was the constant volume case. So you have to use CV. The question, N is the number of moles, just like in the gas law, PV equals nRT. So 2 moles. .5 joules per mole per degree Kelvin. And there's 2 ways of filling that in. It says this is helium. Helium is a monatomic gas, so you can just use 3/2 times the gas law constant, or you go to that table that's on one of the back pages of your reference handout, and you look up helium, and you get 12.5. Temperature change, 100 kelvins. Now maybe I should explain that, because it says in the question, raise the temperature by 100 degrees Celsius. So I'm sure there is somebody watching this who, if I had asked them to do this problem themselves, would have been adding 273 to that. It's delta T, okay? T final minus T initial. If you add 273 to this, and also add 273 to that, it drops out. Celsius and Kelvin are interchangeable when it's delta T, okay? Like if you go from the freezing to the boiling point, that's a change of 100 degrees. 0 to 100 Celsius, delta T equals 100. 273 to 373 Kelvin, that's a change of 100. When it's just plain T, the temperature itself, you'd have to add 273. But temperature changes are the same on both scales. So Celsius, Kelvin, same thing when it's delta T. Multiply it out, 2,500 joules. Part B. This time it's the same thing, except it's a constant pressure. So NCP times delta T. Again, 2 moles for N. This time CP is 20.8, which again, you can either use the 5/2 R, or you go to the table and you look up helium. It's got a column for CP and it's got a column for CV. Temperature change is 100 degrees, and that's going to be 4,160 joules. To cause the same temperature change for the same amount of gas. Okay, what's next? Thermodynamic processes. Adiabatic, isothermal, isobaric. Today's vocabulary words. An isobaric process is constant pressure. Isothermal means constant temperature. Adiabatic means no heat flow. It is often useful to represent processes such as these on a graph. I mean, you must have caught on by now to the fact that graphs are handy things in general, whether you're talking about motion or electricity or, in this case, thermodynamics. And the graph that's usually a useful thing to think about in thermodynamics is a graph of pressure on the vertical axis and volume on the horizontal axis, like this. Now, if you're sneaky about it, you can also, oops, there we go, that looks better like that, doesn't it? If you're sneaky about it, you can also represent a third variable on this two-dimensional graph, the temperature. I mean, maybe the obvious thing to do is just have a temperature axis this way that's perpendicular to the other two, and if you like to build three-dimensional models, you can do that. But if you want to do it all on a sheet of paper, here's the trick. I'm going to draw some curves of constant temperature across this graph, something like, I'm probably not doing this very accurately. Yeah, that part there is especially bad. These are called isotherms. If you take the gas law, PV equals nRT. If you want to consider a constant temperature process, well, an isothermal process, the temperature would be constant. The gas law constant is constant. And if the system doesn't leak, N is constant. So you have the special case of the gas law that's called Boyle's law, PV equals a constant. Or rearranging it a little bit, P equals this constant, the constant that's equal to nRT, divided by V. Well, maybe you remember from a math class what the graph of, I'll just kind of sketch it down here in the corner real small. This is y and this is x. Remember y equals 1 over x? It's a rectangular hyperbola. It's got an asymptote against the y-axis. It's got an asymptote against the x-axis. Well, y equals 1 over x, p equals some constant over v. It's the same thing, except, well, maybe the constant isn't 1, but that doesn't change the basic nature of the graph. You've got hyperbolas here. Hyperbolas with asymptotes against the horizontal and vertical axes. Now, the value of the constant depends on the temperature. So if the temperature of the gas is T1, then you'd have this hyperbola here. If the temperature of the gas is T2, then you'd have that one there. And if the temperature of the gas is T3, that creates yet another value for this constant, which would give you this one here. So if you have some point plotted on the graph, like say right there, you can read off of the graph the volume of the gas. I'll call that V initial because I'm going to talk about changing it in a moment. And you can read the pressure off of the graph because the point lines up with that much pressure right there. And by which of the isotherms that point sits on, you could read the temperature off of there. 3 variables off a two-dimensional graph because they're not all independent of each other. They're linked by the gas law. So You're going to have to write kind of small. But I want to show you what each of these three kinds of processes look like. So if this is point A, we have some gas in a cylinder with a piston, and this is its initial state, its initial pressure, volume, and temperature. First of all, if you reduce the volume isobarically, which is not the most realistic thing, compared to what goes on in an actual running engine, but the nice thing about an isobaric process is that the math is simple. Okay, you've got a constant pressure, you don't need any integrals, and so that would just be a horizontal line, which would take me to about here, I guess. So if that's point B, the state of the gas changes from A to B by following that path right there. And so AB is an isobaric. I should probably print it so you can read my writing. An isobaric, since it's getting smaller, I'll call it an isobaric compression. If the arrow was the other way around, it would be an isobaric expansion. Now, notice that in this case, the temperature of the gas goes down. If you're going to keep a constant pressure, that goes back to what I was saying last time around. You keep a constant force distributed over the area of the piston, constant force per unit area, that's what we're talking about. The way to get the volume to go down is you cool it off. That'll make the gas contract, okay? And if you heat it up, that'll make the gas expand. So lower the temperature and the volume contracts down to V final is right there. Next thing I'm going to put on the graph, I'll label a point C, and the path from A to point C will be an isothermal compression. Isothermal compression. Well, these hyperbolas I drew on here are isotherms. So obviously an isothermal compression is going to follow one of those. And it looks like if I'm going to line up with the same final volume, that should be right about there. So and since it's an isotherm, when it gets here, it's the same temperature it started out with. But it'll be a higher volume. No, I said that wrong. It'll be a smaller volume because you're compressing it. It'll be a higher pressure. The thing I was pointing at was right, just the thing that came out of my mouth wasn't. But you compress the gas and crowd the molecules closer together, and so you get more collisions per unit area, which gives you more force per unit area, so you have a higher pressure. But the molecules are moving just as fast in the end as they were in the beginning, because it's a constant temperature. Temperature is the average kinetic energy per molecule. Well, finally, we have the adiabatic compression from this initial to this same initial volume, and I'm going to have a point D on there in a moment. People frequently want to get adiabatic and isothermal mixed up with each other. Well, let's see. No temperature change, no heat flow. It's the same thing, right? Well, actually, they're more like opposites than the same thing. If you've got, here's my cylinder with a piston again. If you want to have an isothermal compression, what you do is you surround that with something, you put it in what's called a heat sink, okay? A swimming pool with about 20,000 gallons of water in it would work really well, because you can put a significant amount of heat into 20,000 gallons of water and create no noticeable temperature change, okay? So it can soak up heat, it can give off heat and maintain a constant temperature as it does it. So you throw this in your swimming pool, and then you push the piston inward really, really, really slowly. And as you compress the gas, well, compressing a gas tends to raise the temperature because of the work you're doing on it. But as soon as that goes up just a tiny fraction of a degree, the temperature gradient you've created makes heat flow outward through the walls of the cylinder into the surrounding heat sink, and you maintain a constant temperature that way. So an isothermal process is compress it really slowly in contact, good thermal contact with something that can soak up a lot of heat. An adiabatic process is exactly the opposite. If you want no heat flow, the thing to do is wrap that in about 6 feet of fiberglass insulation instead of throwing it in your swimming pool. And then when you go to push in the piston, do it really fast, because that gives the heat no time to flow. So you see what happens in the isothermal case is that you're adding to the internal energy by doing work as you push the piston inward. And at the same time that energy comes in the form of work, energy leaves in the form of heat flow, and so the internal energy stays constant. In an adiabatic process, on the other hand, you're once again adding energy as you do work, but you don't let any of it leave. So the internal energy ends up higher than when you started, which is to say the temperature ends up higher than you started. You're up here at T3 this time. And of course, at a higher temperature, you'd have a still higher pressure than what you end up with in the isothermal case. And the path from A to D would look something kind of like this. Once again, something that's got asymptotes against both axes, but it's not a hyperbola this time. It's something steeper, okay? So it is useful to have equations that represent this graph, and this graph. Pictures are all well and good. Pictures are especially good things to have in your head as you're thinking about things. But when you go to solve a problem, you want to represent that with some sort of quantitative expression rather than just a picture. So let's list out equations. First of all, simplest one is for the isobaric process. Maybe I'll put down what the word means once again. Isobaric is constant pressure. In other words, no change in pressure. Equations don't really get much simpler than that. Back to the graph here. It's a horizontal line. If if it's 100 kilopascals here and 100 kilopascals there and 100 kilopascals everywhere in between, your equation is just simply P equals 100 kilopascals. And I don't really need to say any more about that, I don't think. For the isothermal case, which is constant temperature, in other words, delta T is equal to 0, and along with that, change in the internal energy also. Well, I sort of already covered that on the side of the page over here, but one more time, from PV equals nRT, if it's isothermal, all of that is constant. So for this one, P is a constant. For this one, P times V is a constant. That would be that hyperbolic relationship like I was talking about before. Well, what about an adiabatic process? Yeah, we're not going to come up with that in one line like I did, or one or two lines like I did these other things. That's going to take a little bit of explaining. The word adiabatic, once again, means Q equals 0, no heat flow. So, once again, as with several other things I've shown you, this is going to come from combining PV equals nRT with the first law of thermodynamics. Let's start out with P times V equals nRT. And since we want to consider changes in the state variables here, the pressure and volume and so on, we'll take the differential. Incidentally, when you get into lab 13, gathering the data doesn't take very long. It's probably, I don't know exactly how many minutes, but it's probably a pretty brief video. The calculations take a little more time, and they kind of resemble this sort of thing here, where you have to take differentials and then substitute this thing. And it's not the same exact calculation I'm doing here. It's just the same general type of thing that you're going to be asked to do for the lab. So, product rule. First times the differential of the second plus the second times the differential of the first. Maybe I'll even write that down. N and R are constants, so over here you just got NR times dt. So we need a substitution, too many variables. I want to get everything in terms of pressure and volume. Once I've got it down to 2 variables, then I can integrate. But right now I've got 3, pressure, volume, and temperature. So I need some sort of substitution for dt. We'll get that from the first law, which in general says that delta E equals Q plus W, but we're considering an adiabatic process. The word adiabatic means Q equals 0. So I'm going to set Q equal to 0. And so the first law tells me the change in internal energy is equal to the work done as the gas expands. Now, I'd said previously that the change in internal energy is equal to N times CV times the change in temperature. And I've also said previously that work done in a small changes of state, a little differential change of state, is minus P times dV. So that means that if that equals that, dt okay, there's my substitution. I can put that in there, and that'll get rid of the dt and have everything in terms of pressure and volume. So P dV plus V dP equals nR times the thing from there. Simplify it a little bit. If you notice, those n's cancel each other. And we can clean it up some more if I divide through the equation by P times V. So in this first term here, P dV divided by PV, well, P over P is going to cancel out, and I'm going to have dV over V. In the second term, V dP divided by PV, well, V over V is going to cancel out. I'll have dP over P. Now the variables are separating nicely. And it's always kind of convenient and neat and tidy to throw all the constants together in one little lump. So the R and the CV and the minus sign. And then over here, PdV over PV would be just like it was over here, PdV over dV. It's going to be, well, I've got two terms that have dV over V in them. I think I would do well to combine them. So I'm going to add that to both sides. Kind of did two things at once. I added this term to both sides, and then I factored out the dV over V. So dV over V times 1 is this, dV over V times that is this. Let me play with this constant here a little bit and see if I can make that a little bit nicer. I had mentioned earlier that the gas law constant, R is the gas law constant, is equal to Cp minus Cv of course Cv over Cv is equal to 1, and so that cancels out, and so this constant is the ratio of the specific heat, Cp over Cv. Define gamma, third letter of the Greek alphabet. Rather than write this ratio over and Cp over Cv, rather than writing that over and over again, somebody thought it might be a good idea to just have a symbol to stand for that. So why not the Greek letter gamma? You got a better idea? That would be the general definition. I'll just kind of put in parentheses that if you're talking about a monatomic gas like helium, Cp is 5 halves R, and Cv is 3 halves R. So the ratio would be 5/3. And if you look up, that's the third column in the table. The table where you looked up, there was a column for Cp, there was a column for Cv, and then there was a third column I hadn't explained yet. That's gamma. It's the ratio of the other things in the other two columns. And if you look up helium or argon or any of those, sure enough, it's either equal to or at least very close to 1.67. For other gases, you'll get other values, like diatomic gases are around 1.4, for example. So anyhow, having introduced that symbol, dV over V times gamma, maybe I'll write it in front, plus dP over P is equal to 0. Well, I have finally manipulated it around to where it's all ready to integrate. dV over V, of course, is the log of V. We're going to do it as an indefinite integral this time. And the integral of dP over P is the log of P. And when you do an indefinite integral, you can't forget the constant of integration. Which I had better clearly label, otherwise somebody might think it's specific heat or the speed of light or capacitance or, well, what other things have we used the letter C for? Anyhow, that's supposed to be a constant of integration. Properties of logarithms. Gamma times the log of V would be the log of V to the gamma power, using one property of logarithms. Using another property of logarithms, we have that. And then finally, to get the log off of there, take e to both sides. And that's the thing I've been building toward for the last, I don't know, 10 or 15 minutes or whatever it's been. This constant would be e to that constant, okay? And this is, maybe I should label it, this is for an adiabatic process. So this relationship, where'd the page with my graph go? This relationship is to this curve what this relationship is to that curve. This is to an adiabatic process what Boyle's law is to an isothermal process. Now, what if you don't have, what if you're not interested in pressure and volume? What if you're interested in temperature and volume? Well, I think I've shown you enough details for one day, so I'm going to skip over a few more lines of justification and just jump right straight to the thing with the box around it. From this, together with PV equals nRT, you substitute this into there, and you do a couple lines of algebra, and you can show that T, the absolute temperature, times V to the gamma minus 1 power So if it's a monatomic gas, here you'd be raising the volume to the 1.67 power. Here you'd be raising the volume to the 0.67 power. This would not necessarily be the same constant as that one. And so there's all the theoretical background, and I think right about there is a good place to leave it off for today. And when I get back to the next recording, what follows next is so 3 examples where we do something a little bit on the concrete side with all of this. Bye for now.